Good morning, all of you. Today, I am going to make an audio recording for visually impaired students of Physical Chemistry book of K.L. Kapoor, Volume 1. Name of the chapter is Gaseous State. Gaseous State, Chapter 1. First heading, The Three States of Matter. Introduction. In order to determine experimentally the properties of substance, we deal with the aggregates of molecules as they occur in nature. It is the aggregations of molecules which come within the scope of human experience that constitute what is known as matter. The various kinds of substances that make up matter can be divided roughly into three categories, namely gases, liquids, and solids. These are called the three states of matter. These states can be considered to arise as a result of competition between two opposing molecular forces, namely the forces of attraction, which tends to hold the molecule together, and the disruptive forces due to thermal energy of molecules. Gaseous state. If the thermal energy is much greater than the forces of attraction, then we have matter in its gaseous state. Molecules in the gaseous state move with very large speeds, and the forces of attraction amongst them are not sufficient to bind the molecules at one place, with the result that the molecules move practically independent of one another. Because of this feature, gases are characterized by marked sensitivity of volume change with change in temperature and pressure. There exists no boundary surface, and therefore gases tend to fill completely any available space, resulting in no fixed volume to the gaseous state. Liquid state. If the forces of attraction are greater than the thermal energy, we have matter in the liquid state. Molecules in the liquid state too have kinetic energy, but they cannot go very far away because of the larger forces of attraction amongst them. Due to this feature, liquids have definite volume but no definite shape. They take the shape of the vessel in which they are placed. In general, liquids are more dense and less compressible than gases. Now, solid state. If the forces of attraction between molecules are much greater than the thermal energy, the positions of the molecules remain fixed, and we have matter in the solid state. The molecules in the solid state, therefore, do not possess any translational energy but have only vibrational energy. Since they can vibrate about their mean positions, extremely large forces of attraction exist amongst them. That is why solids differ markedly from liquids and gases in respect of size, shape, and volume. Solids in general have definite shape, size, and volume. Now, the comments on the gaseous system. Of all the three states of molecular aggregation, only the gaseous state allows a comparatively simple quantitative description. We are generally concerned with the relations among four properties, namely mass, pressure, volume, and the temperature. A system is in a definite state or condition when all the properties of the system have definite values. It is not necessary to specify each and every property of the matter as these are interrelated. The relationship which connects The above four variables is known as the equation of state of the system. For gases, only three of these must be specified to describe the state. The fourth automatically has a fixed value and can be calculated from the equation of state established from the experimental behavior of the system. Next topic 1.2, experimentally derived gaseous laws. First is the Boyles law. Boyles law. At constant temperature, the volume of a definite mass of a gas is inversely proportional to its pressure, that is V, sign of proportionality 1 by P, that is V is equal to K upon P, or PV is equal to K, equation number 1.2.1, where K is a constant whose value depends upon number 1, nature of the gas, number 2, temperature of the gas, number 3, mass of the gas. For a given mass of a gas at constant temperature, Boyle's law gives P1 V1 is equal to P2 V2, where V1 and V2 are volumes at pressure P1 and P2 respectively. Graphical representation of the Boyle's law. Equation 1.2.1 can be represented graphically by plotting pressures as ordinates, means along the y-axis, and corresponding volumes as abscissa along the x-axis as given in the figure 1.2.1. The nature of the curve is a rectangular hyperbola. The general term isothermal or isotherm, meaning at constant temperature, is used to describe these plots. Next, the Charles law. Charles made measurements of the volume of a fixed mass of a gas at various temperatures under the condition of constant pressure and found that the volume of the gas is a linear function of its Celsius temperature. This can be expressed as Vt is equal to A plus Bt, where T is Celsius temperature and A and B are constant. Graphical representation. The above equation has been plotted. The intercept of the vertical axis is A and its value to V naught, the volume at 0 degrees Celsius. The slope of the plot is the derivative. B is equal to curly Vt divided by curly T at constant pressure, where the value of the slope is equal to curly Vt divided by curly T at constant pressure, and it is also equal to V naught oblique 273.15 divided by 1 degree Celsius. Alternate form of Charles' law. Experimental data shows that for every Celsius degree rise in temperature, the volume of a gas expands 1 upon 273.15 of its volume at 0 degrees Celsius. If V0 is the volume of the gas at 0 degrees Celsius, then B is given by B equal to V naught oblique 273.15 divided by 1 degree Celsius. With this, the equation now becomes Vt is equal to V naught plus V naught oblique 273.15 divided by 1 degree Celsius multiplied by small t, or Vt is equal to V0 bracket start 1 plus T degree Celsius divided by 273.15, and it is also equal to V naught bracket start 273.15 plus T degree Celsius divided by 273.15 bracket closed, or Vt is equal to V0 multiplied by temperature in Kelvin divided by 273.15, where T is the temperature in Kelvin. It is convenient to use the absolute temperature scale on which temperatures are measured in Kelvin, which is represented by capital K. A reading on this scale is obtained by adding 273.15 to the Celsius value. The temperature on the Kelvin scale is denoted by capital T. Thus, temperature in Kelvin is equal to 273.15 plus small t, that is the temperature in degree Celsius. That is, Vt is equal to bracket start V naught divided by 273.15 in Kelvin bracket closed multiplied by capital T. Since V naught, the volume of the gas at 0 degrees Celsius, has a constant value at a given pressure, the above relation can be expressed as V is equal to K2T, where K2 is a constant whose value depends upon the nature, mass, and the pressure of the gas. The above equation is an alternative form of Charles' law, according to which the volume of a given mass of a gas at constant pressure is directly proportional to its Kelvin temperature. Graphical representation. A typical variation of volume of a gas with change in its Kelvin temperature is shown in the figure. The general term isobar, which means at constant pressure, is assigned to these plots. Now the comment on 0 Kelvin. Since volume is directly proportional to Kelvin temperature, the volume of a gas should theoretically be 0 at Kelvin 0. However, gases liquefy and then solidify before this low temperature is reached. In fact, no substance exists as a gas at a temperature near Kelvin 0, though the straight line plots can be extrapolated to 0 volume. The temperature that corresponds to 0 volume is minus 273.15 degrees Celsius. Gay-Lussac law means dependence of pressure on temperature. An expression similar to volume dependence of gas on temperature has been derived for the pressure dependence also. The pressure of a given mass of a gas at constant volume varies linearly with Celsius temperature. Pt is equal to A plus Bt, where A is equal to P naught and B is equal to curly Pt divided by curly T at constant volume. The value of the latter can be determined experimentally, and it is found to be P naught divided by 273.15. Thus, the above equation modified to Pt is equal to P naught plus bracket start P naught divided by 273.15 multiplied by temperature in degrees Celsius. Therefore, Pt is equal to P naught bracket start 273.15 plus temperature in degrees Celsius divided by 273.15 bracket closed, and it is also equal to, means Pt equal to bracket start P naught divided by 273.15 in Kelvin bracket close multiplied by temperature T, capital T, or Pt is directly proportional to capital T. That is, the pressure of a given mass of a gas at constant volume is directly proportional to its Kelvin temperature. Now the graphical representation of Gay-Lussac law. The above equations are shown graphically in the figures. The general term isocohort, meaning at constant temperature, is given in the plots, where the slope is given by curly Pt divided by curly T at constant volume, and the slope is also equal to P naught oblique 273 divided by 1 degree Celsius. Next, Graham's law of diffusion. The phenomena of diffusion may be described as a tendency for any substance to spread uniformly throughout the space available to it. Diffusion through fine pore is called effusion. According to Graham's law of diffusion, the rate of diffusion or effusion of a gas is inversely proportional to the square root of its density or molar mass. If R1 and R2 are the rates of diffusion of two gases whose densities under the given conditions are D1 and D2 respectively, then from Graham's law, R1 divided by R2 is equal to square root of D2 divided by D1, or R1 divided by R2 is equal to square root of capital M2 divided by capital M1, where M1 and M2 are the respective molar masses of the two gases. Thank you. That's all about today's audio lecture. In the next lecture, we will proceed further about the gaseous state. Thank you.